I will call this the development or creation of smart materials that think. And we're coming from a very different background from your lab, and you have very unique experiences and insights that are likewise very informative for my lab's activities. So I really look forward to hearing your feedback and some of your thoughts about what we're working on. So let's kind of walk through it. What are we inspired by? I get inspired by very simple things: a door latch, a light switch, or as our lab is starting to move more and more in this area, I'm getting really inspired by very simple processes in nature. A spider weaving a web is a great example. It's a control system. It recognizes failures. It tries again. It's not doing something all that complicated, but after a length of time has passed, it has created something that's awfully intricate and specialized. So what does this relatively simple biological system tell us? Well, it constitutes an assembly of a number of very key functions, one of which is a simple way of deciding things based on input that is coming to it and a knowledge of a goal, or you could call it the programming of a goal. In that case, it would to weave a web, and after it has weaved its web, you could consider that system to have programmed a new function, which is to collect food using the web, and so on and so forth. So very rudimentary decision making. It has a means of converting energy in its environment to fuel itself for a while. It has a structure and a frame, so it's got a body. It has sensors and it has actuators. Life forms possess these functions. There are three others. One is the generation of waste, one is growth, and one is reproduction. We won't really reference those because those aren't essential for life, at least life in terms of the engineered sense. Because my question I've been asking for quite some time is, can we engineer life? Because when you look at the functions that are shown there in the column, basically they've all been created by engineers and scientists over the years. And from my vantage point, coming from much more of a mechanics and a materials area, what is really, really lacking is the first entry, the decision-making apparatus that really does not exist outside of the cellular community, cellular world and research field. In mechanics and materials, most often people resort to silicon microprocessors because they're thinking about robotics. But if you could create soft engineered life, there's a whole realm of things you could do. These machines, these systems, materials could support and assist life to be cleaner, healthier, safer, more sustainable, and better for growing. So our lab is really focused to synthesize these 5 functions into autonomous engineered matter, especially soft matter. And what I'll share about in this presentation is our first embodiment where we synthesize sensory signals that automatically control a decision-making system in the machine, and it has a frame. I've got students working right now on both the fueling and the actuation sides, where we could really create an autonomous soft machine with recognition of mechanical input. So the mechanical stress field is a sensory information that concurrently is used to decide things. So how do we do it? It started with a switch, and it started somewhat accidentally. I was working on this in about 2018, early 2019, where we have this polymer. So it's a urethane rubber substrate that's in that green color. And on the surface of it, we had silver TPU. So TPU is thermoplastic polyurethane. It's mixed with silver microflake at about 35%. No, wait, that's by volume. I don't even want to say the mass percentage because I know it by volume. But it's mixed, it cures, and it bonds perfectly to the urethane substrate. This is, in fact, one of the early sloppy samples. It's not very clean in its fabrication, but it works for what it does. And what does it do? Oh, this specific shape of the diamonds and diamond voids and square masses, it rotates. It's actually kinematic in that design. There is a large amount of research in mathematics and mechanics where they're looking at rotating tessellations. And in this case, this material is auxetic because when you apply a force, it contracts laterally rather than expand laterally. Ordinarily, you take a block of material, you compress it, and it bulges. And that's a positive Poisson's ratio. This material has a negative Poisson's ratio because you compress it and it contracts. But not only does it contract, we've chosen a tiling of these geometric shapes so that when it contracts, laterally, it actually fully compacts. And this was a first light bulb moment for us because we realized that if we have materials that, when stressed, create connectivity among the masses, that means we could apply these networks in ways so that they electrically connect. And that's what the image shows. The lights are on through, there's a circuit that is in series with the AGTPU, the silver TPU. And when it connects, it conducts. So this was our first happenstance. It's a mostly kinematic reconfiguration. So you could realize this even in optics, electromagnetics, and so on if you had things that physically moved due to some force field, whether it's a magnetic field, optical perturbations, and so on. This video just shows it in practice. The modulus of the material has a Shore hardness of 68, so it's pretty stiff, not terribly stiff, but you can use things that are much softer, closer to modulus of skin, down to about 10 kPa modulus. But currently this has, I guess, the modulus at 60A Shore hardness. That's closer to about 2 megapascals. But yeah, you can reduce it dramatically down to more biologically compatible materials. So when we did this, we realized we have a switching circuit, and we were interested for a while of studying these switching circuits. And my one PhD student, Charles, and I'll show him at the end, he had an idea of, well, logic gates are one mode of switching circuits. So he thought, could we make a logic gate? The most elementary one is the buffer gate. When the input A is 1, the output Q is 1. VCC is just a control input that always powers it. Vice versa, when the input A is 0, the output is 0. So the buffer gate basically says yes for a yes input and says no for a no input. And in soft matter, the way we realized to do this is to use our construct of these connecting circuits, but cut them. So rather than having the auxetic behavior, now they conserve their area through two separate collapse modes, one due to shear to the right, which we call an input of 0. So if you have a keyboard of some way that you could shear it in different directions, shear to the right means that it is an input of 0, and shear to the left means that it is an input of 1. And we created a AGTPU network on top of that pattern that agrees with that input-output sequence. And so we created our buffer gate, which agrees exactly with what we would expect from a conventional electronic, silicon-based buffer gate. The NOT gate is the inversion of the buffer. All of the sequences are reversed. So we created the NOT gate by mirroring it. And this was kind of interesting because it's very intuitive. If you mirror it, the outputs and inputs, the outputs would all be reversed from the outputs of the buffer gate. And surely enough, this works. This also agrees with De Morgan's theorem. De Morgan's theorem is one of the foundations of digital logic development. It tells us about inversions of logic processes and what they should yield. And so this is more of a mathematical construct than it is a physical construct, but we realize the physical embodiment of it here using our material framework. So this is a video that just shows it. Rotation, shear to the right, which is an input of 0, connects. Let me repeat it. So shear to the right is an input of 0, but it outputs 1. Shear to the left is an input of 0, but an input of 1 and output 0. So that's the NOT gate. Show it once more. Very elementary, right? We likewise thought so, until we found that it kept scaling. So we found that we could assemble all of the conventional logic gates using Boolean algebra and De Morgan's theorem. And the AND gate steps this up. So the AND gate, when you draw it as a sequence of electrical circuits, it is a serial combination of switching circuits. So here what you see is that we have an input VCC, the cyan circle. It has a gate, a switch, and it is in series with a second switch on the next layer. So each layer of rotation or shear corresponds to a digital input. So if you're going to shear it with two buttons from the side, those would be your two buttons of mechanical binary input. And so what we'll see here is a video that shows the layer rotations, the layer rotations at the top left along with the output. So I'll play it again. In fact, I'll play it a few times so we can all appreciate what's going on here. This is an AND gate. So according to the truth table, only when both A and B are 1 will the output be 1. And an input of 1 is a shear to the left. So both the top and bottom layers need to shear to the left for this to be emitting an output of 1. So 0, 0, 0, 1, 1, 1, 1, 0, 0, and 0, 1, 0. It works. Now I'll show it once more. So this is the AND gate in action. Both inputs are 0, the output is 0. Both inputs are 1 because they're shear to the left, output's 1. Shear to the left and shear to the right leads to a 0 output. Shear to the right, shear to the left also leads to a 0 output. I mentioned we found it kept scaling. So it also works for the OR gate. The OR gate in practice is a parallel combination of switches. If you look at textbooks of digital logic. So here we have an input. One switch goes to the top layer and then to the output. The second switch goes to the bottom layer and then to the output. There's the truth table, and here is it in action. 0, 0, 0, 1, 1, 1, 1, 0, 1, and then 0, 1, 1. So when either the top or bottom switches conduct, it leads an output of 1. And of course, when they both conduct, it also leads to an output of 1. So this is the OR gate. So in fact, if we just stopped here, that would be great. But the reality is there are a lot of people who have done this. There are many, many, many people who've done the buffer gate, NOT gate, AND gate, OR gate. Why? Because they're pretty symmetric. And when it comes to creating embodiments of it in other frameworks, people have done this with thermochromatic materials, optical materials, other our example, mechanical metamaterials. There are a lot of examples actually of those 4 gates. But we found that it keeps working. Our concept continues to work regardless of how you scale it. So this is an XNOR gate. So the truth table of that is that only when both inputs are the same does it output 1. And when the inputs are different, it outputs 0. So 0, 0 conducts, 1, 1 conducts, 1, 0 does not conduct, and 0, 1 does not conduct. So long story short, we found that what we started studying realizes all of Boolean logic in soft matter. And we continue to work on this with this vision in mind of creating engineered materials that live. Your lab is likewise very focused on that. And we are interested in doing this in a different physical scale with different tools, but we have very similar goals for autonomous engineered materials and structures. We continue to look for ways to create this genuinely autonomous system, because what I just shared was just the decision-making sensory of mechanical input and then the actual embodiment. Where are we going with this? Well, in a more nefarious sense, we could create Cylons, which a lot of sci-fi fans like myself would appreciate that, but there are a lot of more societally beneficial ways of creating soft living machines, things that collect waste, things that are able to assist in wound healing, and so on. So I said we found it kept working. And I'll give you a little glimpse of what we're working on right now. Not only do the logic gates all compute, we very recently found, as in a couple weeks ago, we found how to make circuits and how to keep adding up to circuits. So this is a 4-bit calculator. Using two 4-bit numbers, it will add up the correct sequence. Only last week, and I didn't have a chance to add it to the slides, but only last week did we take video and everything to show this functioning in the lab, but we do have some of the units. This doesn't have the silver TPU bonded to it yet, but the 4-bit adder, 4-bit calculator is a collection of these full adders. What you see here is called a full adder circuit. It is the foundation for arithmetic in calculators. And they are of course, handheld calculators. The sensory or the information processing of a calculator is of course an ARM chip or something extremely small that's been miniaturized down to a microscale. But in our embodiment, this is a full adder. And when you put them all into this configuration, you can add up 4-bit numbers and it works. So it seems a little bit sci-fi, I suppose. But we're using this type of mechanical matter, smart mechanical matter. We're folding it, we're shearing it, and we're using electrical stimuli to help ultimately process the concurrent amalgamation of mechanical and electrical stimuli. And that seems quite, abstracted. I would likewise say that a brain is awfully abstracted. A sequence of mechanical folds that are there for sake of both memory and computing, and then mechanical electrical stimuli propagate through this system. I'm not a neurologist by any means. But I think there is a little bit of an analogy of where we're going. We also have an embodiment of memory that we're working on, which is probably still too new to share. But yeah, I think we're finding through very, very closely studying conventional circuit synthesis, which we do study quite a lot, just conventional electrical engineering textbooks and whatnot, we're finding that all of this scales in exactly the same way that silicon microprocessors are developed. And I really want to credit one student and more recently other students, but especially Charles Elhulu, who helped get this off the ground, and support from the Air Force Research Lab, who have been integral for some of the initial funding of this, which has been gradually growing in our lab. I really want to thank you for your attention as well. Really looking forward to hearing your feedback because we have similar goals, but very different approaches to what we're implementing. So thank you very much for your attention. I'm all ears for your questions.